thank the organizing committee for this wonderful opportunity to present this work on in this international conference on the Association of Clinical Biochemists of India, the newer trends of biochemistry on ongoing medical sciences. So today I shall be working on yeast derived Glucan particles and how they form a promising approach for therapy for tuberculosis. First, little about the pandemic of tuberculosis. We know that 1/3 of the world's population has been infected with tuberculosis, and about 9 million new cases arise each year. There are about 2 million deaths per annum, and despite the fact that it was declared as a global emergency in 1993 by WHO, and despite the sincere efforts by the government for the eradication of this disease still poses a serious issue amongst the medical scientists. And the situation has worsened with the occurrence of drug resistance, multi-drug resistance, and extensive drug resistance strains of mycobacterial tuberculosis. And apart from that, MDR-TB and HIV co-infection is further weighing the situation. Are the slides changing? Okay. A little about the host macrophage. Normally, macrophages serve as the first line of defense against surviving microbes. In pulmonary TB, the inhaled bacteria are inhaled and taken up by the alveolar macrophages, and they are rapidly phagocytosed by these macrophages, which further modulate the functions to their own advantage. So macrophages serve as primary cells where mycobacteria invades and replicates within imagination-arrested pathogens. The built-in strains of mycobacteria induce alternative activation of the host alveolar macrophage, and that deprives these macrophages of a coordinated defense program against mycobacteria. And this is mediated by various host responses, responses within the host that induce the alternative activation, and that includes the separation of free radical productions, loss and reactive nitrogen species. Other free radicals are suppressed. There is upregulation of anti-inflammatory cytokines in contrast to pro-inflammatory cytokines. And there is promotion of necrosis rather than apoptosis of infected cells. So basically, the host immune response is totally skewed towards an alternative form. In such a situation, targeted delivery of anti-TB drugs to these cells has been shown to form an effective therapeutic approach against tuberculosis. And the targeted delivery offers several advantages. Mainly, targeted delivery is based upon building up drug concentrations within the macrophage, in contrast to the conventional therapy, which is based on delivering oral drugs. And oral drug delivery is based upon building up drug concentrations in the blood. In contrast, targeted delivery would directly deliver the drug to the alveolar macrophages, and that would mean that there would be improved viability of the drug, there would be extended half-life, there would be possibility of controlled release, there would be less of toxicity in the blood, the systemic toxicity all across the body would be lesser, and the drugs would be directly delivered to the site, and therefore they would be more effective. And of course, there would be low drug wastage because the drug is not being wasted out all across the blood. Targeted delivery therefore also results in reduction of drug doses and dosing frequencies, drug toxicity and side effects, and therefore it promises for improved patient compliance. However, there are challenges like selective targeting, drug stability and toxicity. A variety of biodegradable and biocompatible polymers in form of nano and microparticles have been used as drug delivery systems, and among that we chose for beta-glucans. Beta-glucans are biodegradable carbohydrate polymers that are naturally formed in the cells pods of fungi, yeast, algae, lichens, and plants such as rose and barley. So we have been been consuming beta-glucans since time immemorial. Since the time we have been consuming grains, all kinds of grains, including wheat, oat, barley. So, and then another advantage is that beta-glucans also act as pathogen-associated molecular patterns that are recognized by receptors such as leptin-1 and complementary receptor on macrophages. So, beta-glucans also serve as biological response modifiers where they are immunomodulated molecules. This is the structure. Particulate glucan is biodegradable and biocompatible polymer, and it has been granted the generally recognized as safe GRAS status by the Food and Drug Administration Authority. So we decided to prepare beta-glucan particles, and beta-glucan particles from yeast and from both have been prepared also literature. They are prepared by alkaline and acidic hydrolysis. Beta-glucan is found in the cell wall of the yeast cells and can be extracted from there. So alkaline, first these are subjected, the yeast cells are subjected to alkaline treatment, which strips off the nanocylated proteins linked to the cell wall by alkali sensitive bonds, and then it also removes the lipids, cellular lipids that are trapped in the cell wall. These are then centrifuged and then subjected to acidic treatment, HCl around page 5 to 6, and that results in depolymerization and pH dilation, allowing the removal of kite and allowing the removal of kite. So what we get is a yeast wall slurry, and because the cell wall has been, from the cell wall the chitin has been removed, proteins and lipids have been removed, so all the other cellular contents are also removed, and what remains is a ghost of the cell wall with a structured glucan. Of course, residual mannose and some other carbohydrates, so very small amounts possibly. This is basically by and large the beta-1,3, beta-1,6 glucan, and then it is washed with water and acetone and then spray dry for a fine powder. So this shows the yeast derived beta-glucan particles. The size of these, which are also determined by laser scattering, and the morphological characterization was done by SEM. And you can see here the particle size is around 2 micron to as large as 3 micron. We then validated whether what we are getting is actually particulate glucan or something else, and therefore we subjected these particles to Fourier transform infrared FTIR, and we obtained these bands, and band positions confirm the particulate glucan structure of these particles, and the most prominent of these band at 890 was indicative of beta-glucan, beta-glycosidic bonds, and it indicates the presence of glucans. Then this was subjected to C30 and a mass spectroscopy to get an insight into the primary and secondary structure, and chemical shifts were observed, and that indicated the presence of 6 carbon structure, and there was a small additional peak C6 small signal was also found at C6, and it was a characteristic peak due to beta-1,6 branching, and so this NMR spectrum also confirmed the beta-1,3 glucan structure with 1,6 linked side chains. Now, particulate beta-glucans are known to specifically lead to engagement of leptin-1 receptors on phagocytic cells, and that leads to the recruitment of NADPH oxidase 2 on the membrane of the cell, which is taking up these glucans, or mainly phagocytosing any kind of particles, including bacteria or any other foreign particles. So that leads to the recruitment of NADPH oxidase 2, NOx2, and that leads to the generation of ROS. This is the general mechanism for phagocytosis and the induction of reactive oxygen species that also leads to the formation of phagosomes that later on mature in early endosomes and late endosomes which then fuse with lysosomes forming the phagolysosome. Another mechanism is also known autophagy, in which the escaped bacteria or escaped particles are also taken up into a membrane structure, a membrane structure which is known as autophagosomes, and these then fuse with lysosomes. Know that any proteins, mutated proteins or non-functional proteins and other burnout organelles also fuse with are also sequestered likewise and then fuse with lysosomes, and that leads to the degradation of these. We then studied the ROS invasion by these Glucan particles, exposure of these Glucan particles to the macrophages, and this is the NPT assay, we find this blue color formosite crystals that are observed within these cells, indicating of the production of superoxide. And we also studied in response to this ROS invasion upon phagocytic uptake of the particles, we observed the induction of phagosomal maturation, autophagy, and antimicrobacterial activity. Phagosomal maturation was observed using lysotrapegy and apatine orange. Autophagy induction was observed at the protein level, and antimicrobacterial activity was observed using safety protein. This is we observed that Glucan particle exposure macrophages resulted in the induction of lysosomes accumulation within the cell. There was increased acidification. Again, the protein orange dye explains the nucleus and nucleus as green, and the acidic vesicular organelles are seen as bright red colored substances. So, as we see here, as compared to the control cells, there is increasing accumulation of lysosomes as well as the reduction of formation of acidic vesicular organelles. We saw there was increased production of lysosomes of acidic vesicular organelles at early and late time points, as early as 30 minutes exposure, and late time point was up to 24 hours after exposure. Autophagy induction is also monitored by another marker, which is the occurrence of LC3, light chain 3 on the surface of the phagosomes, and we then also used antibody-mediated monitoring of the LC3, presence of LC3 or the recruitment of LC3 on the phagosomes after uptake of these particles, and we observed that both 30-minute and 24-hour post-exposure time points indicated the presence of induction of LC3, processed LC3 on these phagosomes. And so particulate beta-glucan signaling was seen to induce reactive oxygen species and phagosomal maturation, and also induce autophagy reduction. Now with this background, we again decided to use evaluate these yeast-derived beta-glucan particles as delivery systems, and these bland glucan particles they're used to encapsulate antiviral drug, glucan, which is also used against HIV, and it's a preferred drug for TB-HIV co-infection, and this drug was incorporated into these glucan particles. So we subjected these bland glucan particles, we incubated them with glucan that was dissolved in this buffer at pH 8, and then incubated them. And then these that allowed the entrapment of rifabutin drug across the porous particles into the lumen of the foreign shells. And this was then the addition of this buffer resulted in the precipitation of rifabutin drug within the plant particles. And so we had nano precipitates of rifabutin, and then this was, because this was a porous structure, the drug was likely to move out of the particles as likely it moved into the particles. So this was covered or encapsulated with an additional layer of sodium alginate by using cross-linking calcium chloride. And that led to the final formulation, which was a nano-rifabutin loaded butyl particles. This is a kind of a line diagram showing how these butyl particles are prepared. These are from the yeast cells by alkaline acidic extraction, which is soluble homogenized chloride. The butyl powder we can see here, sizing and shift analysis by SM and laser diffraction, validated by FTIR and NMR, thermodynamic analysis. And then these were lyophilized after evaporation of drug. And then these were again subjected to chem and drug-loading analysis and pharmaceutical uptake and cytotoxic studies. The size and surface characterization of these particles was done for both plant and alginate seed rifabutin loaded butyl particles. And as we can see here, the plant butyl particles showed a average size of 4.1 micron, and the zeta potential was minus 9.46, which further increased to minus 20 because of the additional layer of alginate, the negative charges. And the dynamic light scattering product because of spray drying later on resulted in decrease in size. The final size of the population came out to be 1.41 micron as an average. This is the SEM and chem characterization of particles, and we can see here the plant and the alginate seed butyl particles, and the transmission electron microscopy analysis shows the nanopores on the surface of plant butyl particles, and the alginate seed butyl particles can also be seen with a smooth and glistening surface, indicating the presence of alginate, and also showing these the nanocrystals or the nanoprecipitates of the drug, some on the surface and some would be, many would be in fact loaded within the butyl particles. We also conducted the thermal stability analysis of these particles for pharmaceutical application, and the particles were seen to have a fairly high thermal stability, and we monitored it for temperature ranging from 50 to at least around 300 or 100 or 150 around. So they quite good thermal stability. More than 90% of the formulation was found to be stable. The quantity can be subjected to the analysis of drug. The drug analysis that was analysis for the amount of the drug that was being loaded into the particles. This slide shows the HPLC chromatogram of rifabutin. This is the pure rifabutin. The upper one, and the lower chromatogram indicates the rifabutin that was released from drug-loaded alginate seed particles. And based on that, the quantitative analysis was done, and finally we had this data. We had prepared several batches of butyl particles, but then one of the batch that was prepared by spray drying method and sonication followed by spray drying gave better results, and therefore was selected for further studies. This showed encapsulation efficiency of 80.74% and loading efficiency was 40.49%. This batch was selected for further studies. We also studied the time-dependent release of the drug at various pH, including the acidic pH 5 for the tap indicator of the tabulysosomal pH, and was carried out in acetate buffer at pH 5.2, and also studied the release at pH 7.4. for indicator of the cytosolic pH carried out using phosphate buffer. And it was seen that there was significant drug release. In fact, the drug release at pH 5.2 was slightly faster as compared to that at pH 7.4, and we studied the drug release for up to 72 hours. And after that, we also try to fit it in a more mathematical model, so we put drug release data over 72 hours, and our data showed that while the drug release was mediated by diffusion, it followed the first order kinetics, that was concentration dependent, and it showed best fit to the UG model, again indicating the diffusion control drug release from these particles. The particles were found to be readily taken up by the macrophages. Macrophages, uninfected and mycobacteria infected macrophages. Both the macrophages were capable of readily taking up these particles, and regarding the toxicity, the particles were found to be fairly non-toxic up to a concentration of 10 microgram per ml. With more than 90% viability of the cells. Increase in the drug concentration above 10 microgram per ml was seen to have a significant increase in toxicity of these cells, and therefore 10 microgram per ml was selected for further studies. Next, we studied the immune responses in mycobacteria infected macrophage, and we studied gross remission by ECFS case study, and while this was studied at various drug concentrations, the 10 microgram per ml concentration was studied for further studies. This slide again shows the induction of reactive oxygen species by these cells. By these cells in response to exposure to glucan particles within uninfected cells and within mycobacterium infected cells, and we found that significant cross relation indicated significant release of significant immune response, and likewise these also induce significant amount of nitric oxide, and again the acetylcholine staining indicated the accumulation of lysosomes and the increase in production of acidic ordinals, accumulation of acidic ordinals within the cell, again indicating high lysosomal activity within these cells. We tried to also explore apoptosis induction by these particles, and we observed that at 10 microgram per ml, there was a slight apoptosis induction, which was comparatively much higher at 100 microgram per ml concentration. Exposure of these particles. Next, we studied the therapeutic efficacy of these glucan particles, and we found that the microbactericidal efficacy of the soluble or the free drug was 2.5 times enhanced by nano-entrapment within these glucan particles. And you can see here, these are this is the control, and we are following it up to 72 hours after exposure of these particles. And exposure to only blank particles without any drug product also had some increase in, also had some antimicrobial efficacy. These nano-formulated glucan particles. So this is the CFU data, and we can observe that this is at the 0 hour time point control, and at 48 hours you can see the reduced number of CFUs, and 72 hours likewise. And so there was a highly significant reduction in these CFUs, of mycobacteria, amounting to 98.7% reduction by 72 hours, at levels even higher than that by soluble solvent at equivalent concentration. Here I must also mention that we took equivalent amount of these drugs by weight. So equivalent amount of when we took plant particles, we took 10 microgram per ml of plant particles. When we took bifidobacter, we took 10 microgram per ml of bifidobacter drug only. And when we took this nano formulation, nano bifidobacter loaded with the isolate C particles, we took again 10 microgram per ml of that, which actually had about 4 microgram per ml of the drug. And this 4 Okay, so should I wind up? Yes, sir. So, okay, so while we are observing this decline in CFU, significant decline in CFU, this amount of 10 microgram per ml of this formulation actually has only 4 microgram per ml of the drug, and therefore is highly significant. So the proposed formulation, to summarize, has uniform porous particles with high drug loading. It targets and activates macrophages. It affects the defense responses of macrophages that are infected with mycobacterial S57RA strains, that is, it reduces reactive oxygen species, nitric oxide, apoptosis, and activates autophagy. And most importantly, it significantly enhances the antimicrobial efficacy of the encapsulated drug. And these results show that this formulation not only activates the mycobacterial infected macrophage, but also significantly adds to the efficacy of the drug, and therefore is a promising approach for as an alternative or adjunct form of EDP. And I just need to acknowledge my team, my research team. Basically, this work was carried out at Kanpur University, and these are my PhD students. I'm trying to extrapolate this work here also. This is Fatima, this is Tarun, this is Visakaksha and Niharika, and I have been collaborating with the CDRI for my work, and the funding from BPCST, the SD Fest, and project from ASD is also acknowledged. And again, I would also like to thank the organizing committee of this conference for giving me this wonderful opportunity to present my research findings. Thank you so much.